Thank you very much, sir. We wish you all a very productive conference with exciting and encouraging discussions and exchange of knowledge so that together we can anticipate a future of groundbreaking research and technology for mankind. May Allah bless us all with good health to make this event a successful and enjoyable one. Thank you so much for your presence and patience over here. Let we have a cup of tea and then we'll join the sessions again at the same place. Thank you so much.
I would like to ask Dr. Ishaq Ahmed. He is Director General, Center of High Energy Physics, National Center for Physics, Islamabad. Dr. Ishaq, and he will talk about accelerator-based methods in investigation of materials.
Bismillahirrahmanirrahim. Assalamu alaikum. Thank you very much for inviting me to here. So first, I would like to thank Professor Zafar Ilyas Sahib to give me opportunity to speak in this forum. So here I would like to speak on accelerator-based methods in investigation of materials. I will discuss about advanced methods. So here mostly accelerator-based are advanced methods which in future surpass other techniques like XRDs, FTIR. I will discuss about in the following slides. So outlines of my presentation is, first I will be discuss about the particle accelerators, then how they work very roughly, evolution, the dawn of particle accelerator, why we need particle accelerator, and where are we now. Second, which type of accelerator I will brief you, and their applications. So you know we have accelerator-based equipment in daily life. In our microwave oven, it is also accelerator-based equipment. For radiation treatments, you can see here radiation treatment, food sterilization using electron beam technique, and you know SEMs. These are equipment used for daily use. So next I will discuss about particle accelerator applications. You can see here cancer therapy, radiology, instrument sterilization, isotope production. These are the main applications. So I will concentrate here only about the material science application of these different type of accelerators. So what is an accelerator? An accelerator, you can see a stationary particle. If we apply electric field, it can get energy and achieve energy to accelerate it in high energy. You can see in the final extremely high energy we can get after apply electric field. This is achieved using electric field for acceleration, and we can also apply magnetic field for control of these ions. So this is the basic concept of accelerator. So I will discuss further here. If we apply, you can see here, if we apply electric field, this ions positive ion get energy and accelerate. So if we increase energy of these ions, we further strengthen the electric field, apply high voltage, electrostatic voltage, or other radio frequency power supplies, then we can high energy electron beam, ions beam or electron beams, which we can call it accelerators. So we can, you can see here, further push it, and then we can get high energy ions beams. These are very useful for material science applications. So this accelerator you can see here in kilometers. Then we can get energy in giga electron volt, mega electron volt. So the size is very high. If we reduce the size, we can use magnetic fields. Here you can see this, it is compact, and we can get high energy ions. So like cyclotrons, synchrotrons, this type of accelerator I will discuss. And you can see here, if we apply 5 volt, we can get 5 electron volt of these ions. So why we need these accelerators? First, you can see Rutherford discovered the nuclear disintegration. These ions, high energy ions, were used for study of the nucleus and nucleon. Inside, we can discuss these effects in following slides. Natural alpha particle, when interact nitrogen atom, it convert into oxygen and we get proton beam. Protons we can get after nuclear reaction take place here in this reaction. This is the natural alpha particle. So interest was increased that if we study the nucleus of different elements, this is for only neutron. This provoke a strong demand for artificial generate high energy beams required to study nuclear physics. So artificial, how can produce it? So the concept was provoked in the scientists, and they think that we can accelerate these ions for high energy to penetrate into the nucleus. Then we can know about the nucleus, then we can study. You can see here, if we have not enough energy, they can scattered from the nucleus. Helium ions, you can see here, back scattered or scattered somewhere. If we have enough energy, you can see here, nuclear reaction take place. We need these high energy ions to penetrate into the nucleus. Then we can know about the nucleus of different ions. Light ions, we almost need low energy, can easily be penetrate. If we need high energy ions, they can penetrate high mass elements like tungsten and gold, easily disintegrate nucleus, and we can get radioactive ion beams or other ion beams. This is the basic concept. We need high energy accelerators. The race was started to develop high power supplies, because high electric field we need to accelerate in the giga electron volt of the ions. So different type of power supplies were developed, which we can say these are the accelerators. So you can see here different type of DC voltage accelerator, DC power supplies, electrostatic accelerators developed. But these have some limitations. We cannot further increase the energy. Therefore, we go to the resonance accelerators. In DC voltage accelerators, we can get maximum 11 or 12 gigavolt, and we can generate energy up to 200, 300 mega electron volt, giga electron volt. If we go further, we need resonance accelerators. It all depends upon the power supplies. So different combination of power supplies, we can increase the energy. We cannot use step-up transformers. They have limitations. We can get maximum 200 kilovolt for step-up transformers. For resonance, we giga, and you can see in this a CERN accelerator where we use about tera electron volt, we can get energy of the protons. So high energy, we need different type of accelerators. So they have different applications. These are linear accelerators. You can see we can increase the energy of the ions, but its drawback is length is about kilometers. You can see here, this is the RF linear accelerators you see here in kilometers range. If we get giga electron volt energy range. If mega electron volt, we can get about, it is enough for 30 meter or 80 meter is enough for to get mega electron volt energy range. If we increase giga electron and more than high, we need too much length we have, then we can get the high energy beam of ions. So these are the circular accelerators. These are different type of accelerator you can see. This is CERN. Circumference is about 27 kilometers. And here we can get about 13 tera electron volt energy of the proton. So the basic concepts for material analysis. You can see here, these are the accelerators for nuclear study. So every techniques have some spin-offs. So when ions interact backscattered, we know the energy of the initial ion. After backscattering, we can calculate the energy of the ions, and we have the formula to calculate that the target atom. Simple elastic collision we can apply here, and we can know which atom is in front of this ion. So every atom have different energies. They are fingerprint of that atom. So we can identify the target atoms. So here you can see when nuclear reaction take place, these gamma rays have characteristic fingerprint of that specific atom. We can identify this atom in our target, in the target of ion beam. So we can identify the atoms. Here you can see X-rays are also fingerprint of elements. And if we increase the energy of electrons close to speed of light, X-rays are emitted. So these are the spin-off used for material analysis. These are the advanced techniques as compared to XRD, FTIR, XPS, and SEM, other techniques, UV visible. So if we use these techniques in your research work, then I hope you can get good research. And these are the future techniques. I will give you some examples in the following slides. This is the basic principle of electrostatic accelerator. If we increase the potential, you can see increase the energy of the ions. And this is our accelerator in NCP, National Center for Physics. You can see when we can accelerate, generate here ions and accelerate, and finally target it in the target chamber. And what you want to extract from this ion-solid interaction. So related to material science, I will give you some applications which we have. This is our accelerator. These are the applications. Elemental analysis. Elemental composition we can extract from these reactions. From these informations we can get elemental composition and depth profiling of individual heavy elements from hydrogen to uranium. This is the technique, non-destructive technique. You can identify hydrogen, which is very difficult from other techniques. So you can use this accelerator, ion beam accelerator, which have these applications. Measure multi-layer thin film thickness. We can measure the thickness of the thin films. Diffusion between two thin films, diffusion with thin film and substrate we can identify. This technique can be used for identifying. So useful for defect evaluation in optical and scintillator crystals. Useful for crystal quality estimations. Ion beam mixing for synthesis thin film coating. Sometimes very difficult to synthesis compounds, alloys using chemical routes. From this route, you can synthesize forcefully, mechanically compound or alloys you can use and beam mixing technique. Phase transformation is possible through this ion-solid interaction. It is possible. And beam induce phase separation and segregation could be possible using high energy ion beams. Nanostructure materials you can synthesize through this ion-solid interaction. aging study of nuclear reactor materials is possible. Radiation damage study of satellite body material. These are the applications of electrostatic accelerators. Wear, friction, corrosion resistance, fatigue, surface modification could be possible through these ion beams. These are the electrostatic applications. I will give you some glimpse about the synchrotron X-ray source. If we increase the energy of electron close to speed of light, X-rays energy dissipate from this acceleration. So this is the Shanghai synchrotron radiation facility in Shanghai. They have broad range of X-rays could be emitted from this synchrotron light source. And you can see the many applications. Basic concept of this photon interaction is fluorescence, absorption, when photon interact with materials, these possible, fluorescence is possible, absorption, photoelectric emissions, reflection, diffraction of the photons, imaging. These are the X-ray source with broad range from about 0.4 kilo electron volt up to 100 kilo electron volt range X-rays we can get from this synchrotron light source. And they have, you can see the brightness flux you can see here, you can compare with X-ray tube. Conventional X-ray tube for XRD study. And we are here. Field emission electron source undulators, we insert devices here to accelerate ions, electrons or proton. We can get high flux, high brightness. I gave you some examples of this accelerator application. These are the many applications. You can use these techniques. I just gave you these advanced techniques for your research projects you can use. Here you can see diffraction, protein crystallography, fluorescence microscopy. These are the different techniques are used for material analysis. Here gave you some example which I have done in Shanghai synchrotron light source. You can see here, basically my work is to irradiate sample nanomaterials or bulk materials with ion beams and observe what happens after ion beam irradiation, before and after. So hexagonal graphite irradiated with carbon ions, and you can see here, this is a conventional XRD spectrum. From synchrotron XRD, you can see these rhombohedral phase also observed clearly. From conventional techniques, XRD, we cannot see any other peaks. So this is the advantage because of brightness of synchrotron light source. In this range, you can see 10 raised to power 21, 10 raised to power third generation, 10 to the power 18 photons. This is the unit of this brightness. These are the application and advantage of synchrotron light source, and they have many applications. Here you can see. And other applications you can see here. This is the normal spectrum you can get from conventional XRD. But these satellite peaks we cannot observe from conventional XRD. What is the advantage of these satellite peaks? Show that crystal lattice expanded along the C-axis of gallium nitride. We irradiated chromium ions into gallium nitride thin films, and we get these satellite peaks using synchrotron X-ray source. So this is the advantage. We can see the bond length we can see through this advanced technique. In other experiment, we have observed also satellite peaks. Here you can see induced scan is assigned to the implantation induced damage as well as the formation of gallium, chromium nitride new compound in the implanted part of the sample. So this type of advanced technique, if we use, we can get published in good journal easily. Second ion source is spallation neutron source. Already NoorMuhammadButt have explained about the application of neutron diffractions and other techniques using reactor technology. But here, spallation neutron sources have a broad range of energies of the neutrons. Through acceleration, we interact high energy protons or heavy ions with solid samples, then we can get different type of energies of the neutrons. And they have multiple applications. I gave you some, I will not go into the detail. Backscattering spectroscopy. These are the beam lines of the neutron source, spallation neutron source. Different diffractometer, high pressure diffractometer, different magnetism reflectometer, liquid reflectometer. These techniques are basically real-time analysis. In molecular level, we can observe the behavior of the materials, and during your chemical reactions, you can even see, you can do chemical reaction in your lab. You can directly go to these facilities and do experiment real time. This technique will tell you what happened, what are going on in these reactions. So these techniques are real time, tell you about the detail of the chemical reactions in molecular level. And other techniques here you can see neutron spin echo. You can study, you can go to the internet, you can find which applications they have, because I don't know enough. I gave you some glimpse about these advanced techniques you can use in your experiments. We can facilitate you, because spallation neutron source, we have collaborations. In China neutron source, you can spallation neutron source and many techniques.
Sir, time.
Achha. And these are the applications of this spallation neutron source in material science. And we have also radioactive N-beam source in CERN. These are also new methods to analyze materials in advance. So this is the recent developed methods. Old methods already exist. So these methods might be useful for your material science. They are exploring using these radioisotopes production by accelerator-based techniques, and these radioisotopes are useful for material analysis as well. So just I gave you some example about the synchrotron. जैसे आपने सर वो देखा होगा कि फार्मेसी में जो साइड इफ़ेक्ट्स होते हैं ना मेडिसिन के, तो कन्वेंशनल टेक्निक से तो वो कोई केमिकल ही होगा ना सर, वो कन्वेंशनल टेक्निक से आपको नज़र नहीं आएगा कि इसमें यही केमिकल अगर रिमूव किया जाए तो वो साइड इफ़ेक्ट्स नहीं होंगे. ये जो सिंक्रोट्रॉन लाइट सोर्स है, इससे वही माइन्यूट सैंपल जो साइड इफ़ेक्ट देते हैं वो आपको उसमें नज़र आ जाएंगे. और जो फार्मास्यूटिकल जो कंपनीज़ हैं वर्ल्ड वाइड अब वही टेक्निक्स यूज़ कर रहे हैं, और हमारे जो फार्मास्यूटिकल कंपनीज़ हैं वो अवेयरनेस नहीं है इन टेक्निक्स के बारे में. तो वो वो कम्पीट अब कैसे करेंगे? वही ख़तरा हो जाता है ना कि फिर हमारी इंडस्ट्री फिर वो डाउन होती जाती है, फिर ख़त्म हो जाती है कि वही जो मेडिसिन हैं वही लोग फिर यूज़ करेंगे जो साइड इफ़ेक्ट्स नहीं देंगे. और यही टेक्निक्स फ्यूचर में यूज़ होनी है मटेरियल के हिसाब से या फार्मास्यूटिकल या बायोलॉजिकल के लिए. तो इन आपसे यही जो स्टूडेंट्स बैठे हैं या प्रोफेसर बैठे हैं, यही रिक्वेस्ट करूँगा कि इन टेक्निक्स की तरफ जाएं, अपने सैम्पल्स डेवलप करें, और ये फैसिलिटेट भी करते हैं आप लोगों को ना कि आप प्रपोजल सबमिट करें। एनसीपी हैं, वहाँ हमारी कोलैबोरेशन हैं, इन सारी स्प्लेशन न्यूट्रॉन सोर्स हो गया, सिंक्रोट्रॉन हो गया, ये जो रेडियो एक्टिव एन बीम्स हैं, आप प्रपोजल जमा करें, हम आपको फैसिलिटेट करेंगे, वहाँ जाके एक्सपेरिमेंट करें, और अच्छे पेपर भी आएंगे, अवेयरनेस भी होगी, एडवांटेज भी होगा इन टेक्निक्स का कि क्या क्या फ़ायदा है। तो इसके लिए वेलकम, जो भी फैसिलिटेशन के लिए हम तैयार बैठे हुए हैं। थैंक यू वेरी मच।
Thank you, Dr. Ishaq Ahmed, for a very informative and detailed talk about the accelerator materials. If you have any questions, only one or two questions, quick ones.
We have had that one example of these high energy sources is measurement of cell thickness.
जी
Measurement of cell thickness.
जी
Do you think that these high energy sources may disturb the surface of area and may damage the surface of?
No, only we have current 12 or 13 nanoampere current of the ions accelerator, so it cannot be damaged. If we increase the current, then it will be possible to damage the surface of the film. Otherwise, can.
Our next speaker is Dr. Sayyid Javed Khurshid. He is an independent think tank professional who served Pakistan Atomic Energy Commission for 40 years as a consultant, advisor, Director General of Planning and Projects, Director Biosciences and Executive Secretary, Abdul Salam International Nathia Gali Summer College. He is working with different think tanks as an expert on nuclear knowledge management and weapons of mass destruction, nuclear energy and climate change. He is a visiting professor at 3 universities. He is a member of the editorial board of Insight International Strategic Studies Institute, Journal of Strategic Vision of SVI, and associate editor of Journal of Pioneering Medicine USA and Journal of Bioterrorism and Biodefense USA, advisor to Al-Muqit Labs Lahore and regional rep at Islamabad, motivational speaker to Siren ICCBS Comstech. So please welcome Professor Dr. Sayyid Javed Khurshid.
Bismillahirrahmanirrahim. When I was coming here, and 2 days ago, Zafar invited me that you might say something in the conference. So the word of smart material really attracted me. And I thought I may speak as a think tank on the smart materials. What are they and what is happening? So instead of speaking on some materials, I give guidelines to the researcher here that the world is open for them and the doors are opening for the material research. I use a very different word. The doors are opening for the material research and basically the smart materials which we are talking, because the whole world is after new technologies, whether it is used in industry or civil or military purposes. Basically, there is a lot of emphasis on using the smart materials for the military purposes. Therefore, I want to give you the thinking that how vast the field is and why we are not working on the smart materials. We should work on the smart materials because the new technologies I have given a word here, new emerging technologies, because all the new emerging technologies which I will show you are going to use the smart materials. Okay, I will start with the thinking. It is decided that mankind has to survive in this world. Okay? When it has to survive, need to achieve, UN has given 17 sustainable development goals to you, SDGs. First there was MDGs, and we were unable to react on MDGs. We were unable to achieve MDGs. Now they have given us 17 sustainable development goals. So if we achieve these 17 sustainable goals, because these goals almost cover everything, the key to all these goals is development. What we go after? We go after the development. Whether we are a scientist, whether we are an economist, whether we are a government official or anything. So we are going for development. And development is needed for the basic poverty elevation. And poverty elevation and all these things are covered by the 17 sustainable goals. For that, what we have to do? We need to control these 17 development goals, or to control the development, we actually need emerging technologies. The word emerging technologies is not a simple word, because there are different categories for the emerging technologies. Nearly, the world has pointed out 80 emerging technologies. Out of 18, they have reduced very essential emerging technologies to 30. Okay, from that they have also reduced it to 9 or 10 technologies which are really needed for the development world, and now for the military purposes and for everything, they need 9 or 10 technologies. And these 9 or 10 technologies depend on new and advanced materials. So you can imagine why the smart materials and new materials or advanced materials, whatever you use the word, is essential for us to work on and to get research done and to get them in production. What I mean, I don't just stop at research. Research is okay. Publications, to get the publications is fine, but unless you bring it into application, you cannot achieve a development. You cannot bring your country up. So just publishing a material is very important, but not very important when I talk about the development. I talk about bringing the country up. In the advanced countries. Why we are not counted in advanced countries? This is the main thing what I'm talking about. Unless we bring it to the practical application, we won't be called as advanced country. Most important area, let's see, what are the most important areas in the coming new emerging technologies and their impact on the safety. When I will talk about new technologies, when I will talk about new materials, when I will talk about new emerging technologies, it is very important to get an idea that beside that, safety and security is one of the important things. Because, see, getting control on the new technologies, getting control of new materials, you have to keep safety and security in your mind. And the procedures first. Okay, what are the emerging technologies? They are technologies whose full potential is still unrealized. We have to see that. Breakthrough on emerging technologies such as artificial intelligence, cyber security, 3D laser printings, drones, biometrics, nanotechnology has already been made, and some more may have been on the way. These technologies are essential for contemporary advances and innovations in various fields of science and technology. The potential benefit of emerging technologies are enormous. Let's see. Artificial intelligence, autonomous systems, robotics, biotechnologies, communication, and networking technologies. These are the things after which advanced countries are going. Human-machine interface. Oh, this is very important. and microelectronics, semiconductors, and microelectronics and space technologies and systems. These technologies relate to including cyber warfare. See how the things are changing, how we are getting near to the very dangerous materials, including cyber warfare. Current weapon systems and existing modernization are human sensors. Okay. Now, in 2022, some more technologies are included in the new technologies. They are hypersonics, directed energy systems, renewable energy storage systems, and nuclear energy. These are recently included in the new technologies. Okay. New materials. Now, we see how the new materials are helping these new technologies. First, I talked about the new technologies. First, I talked about the development, how the development depends on the new technologies. Now I am talking about how the new technologies depend on the new materials, on the smart materials, and how we can support these new technologies. A country must continue to develop new technologies to stay ahead of its adversaries. Means, if we are living in Asia, we have to see what changes in new materials and taking place in India, in China, and people around us. Critical and emerging technologies, we have to discuss that. Advanced computing, advanced engineering material, I pointed out that. Advanced turbine engines technologies, advanced manufacturing, advanced network sensing. Now, the new emerging technologies need innovative materials. So, when we come to innovative materials, what is lacking? Why we are not doing that? Technology today is evolving at a rapid pace, enabling faster change and progress, causing an acceleration of the rate of change. The pace of new material development has increased about 20 times. See, our pace is very slow. Somebody really asked me that how you place Pakistan. See, we are at a very slow pace. And even adopting that pace, we are not able to give this material for the industrial uses. See, if we give this material for the industrial uses, then actually we are progressing. If we are unable to do that, if we are unable to bring the industry towards that, we are not progressing. So, to be a progressing and developing countries, we have to do research like that it should be adopted by the industry. New materials are the key to addressing challenges in energy, health, care, and national security. Healthcare, a little bit pointed out by the MSSM about the nanotechnology, how it is used in the healthcare processes. Now, my emphasis will be like to this talk, because I'm talking broadly, I will say challenges we are facing in energy productions, challenges we are facing in the national security. They depend on the new materials. So are we developing those new materials? We should ask, as a scientist, we should ask this question to ourselves. Are we developing those materials which can be used by the country? Are we developing those materials which can bring us to a developed country? You should ask those questions. The computational, okay. First I pointed out, now it is very fast. Second, I will say the computational predictions are giving acceleration to the material discovery. Have we developed this computational prediction system somewhere in the country which can help the scientists? Material discovery and broader material research community should think about it. The best condition for industry and scientists will be there, should be there, not will be there. Okay, let me give you an example. Using conventional approach, it used to take an average of 15 years, 10 to 15 I will say on the safe side, to conceptualize and commercialize a new material. See, I said commercialize 10 to 15 years. Conceptualize, you can say 5, 6 years, but have you done the commercialization of these materials? Because I'm gauging the research to bring the fruits to the general population. Therefore, I use this word. Now, the supercomputers approach. Now we have supercomputers, and the developing countries are using supercomputers for the material research. Material science has made it easy by removing the guesswork for material design. So now we don't have to guess the work. We should go to the computerization and chalk out what should be the what should you do, and what should be the design, and what should be the things of the material you are working. Now, computer experimentation and characterization enable to develop of a better predictive material models. Advances in material discovery. Now it is easy to evaluate existing experimental data to discover new compounds. The data can help in two ways. Data can be used to refine methods. It will improve models. It will build confidence in predictive models for the users. The database of more than 31,000. There are different database banks, but one which is used in US is nearly 31,000 materials are present on it, and about 5,000 users are using them. And you can see about 20% from industry and 20% from government, and remaining by the researcher. So researchers are using 60% of this data available. Now, I will ask the question afterwards, but I'm just giving an example here. I will mention the recently discovered materials just to see when I was looking that a material is really recently discovered in the material sciences, and that material is an alloy of chromium, cobalt, and nickel. And it can go to minus 4 to 4 Fahrenheit degree centigrade, and is highly malleable, impressively strong. Ductility improves with the temperature going down, and material scientists understand that what I mean. New materials are affecting all aspects of life through innovations that enable, for example, what physical properties and what chemical properties and what transportation properties they have is the things which are bringing this research of new materials up. Strong, lightweight for aerospace applications, clean, accessible for drinking water around the world, superfit computers with vast amount of storage, self-cleaning surfaces, wearable sensors and health monitors, safer foods through packing and monitoring, regrowth of skin, bones, nerve cells for better medical outcomes, smart windows that lighten or darken to convert energy, and nanotechnology enabled concentrate that dries more quickly and has sensors to detect stress or corrosion in roads, bridges, and buildings. Sensors enabling handheld gas sensors, portable bioassays, photonic sensing, electromagnetic field, ultra-fast lasers, enabling tabletop access, sources to provide nanomaterials, resolution, 3D tomography, low-cost photocells, material for fast charging and high energy density, use of carbon nanotubes, yarns in stitched hybrid composite for enabled damages tolerance, nanoparticles for targeted and controlled delivery of images, and advanced for HIV vaccines. They can be used. There are other sides of this materials. I am giving just one example. So they can be used in warfare things. So now we are discussing a lot of nanomaterials in the chemical weapon control systems, chemical weapon conventions, biological weapon conventions, and other uses to make laws for these nanomaterials and nanoparticles and materials of dangerous nature, because they are of dual nature. Dual nature, they can be used for the betterment and they can be used for the dangerous purposes. So there is another side of these nanomaterials you have to understand when you do the research. Materials are far more reactive, unpredictable than normal chemical and biological particles. Nanotechnology has accelerated existing threats and created more novel and more complex threats. A more proactive policy framework is needed for different materials. Here you see, I have used a proactive approach. Why I have used that word proactive approach? When you see in Pakistan, it is not a proactive approach. We have an approach when we get affected by something. So it is a reactive approach, not a proactive approach. And there we are getting negative results in climate change. Because all the approach in the climate change is reactive approach, not the proactive approach. Because we have laws from 2012 in the climate change, but they are not implemented. We use them when we get some disaster. We have a disaster management cell, but it is activated after the things. So it is a reactive approach. There is a need of assessment. Now, when I say that materials can be dangerous, there is a need of assessment of material development and elements to CWC, BWC, Wegener arrangements and UN Resolution 1540. Instead of individual, state parties should be assessment. A formed collective assessment should be made by collective bodies, participated by state parties, policymakers, scientists, industries, and civil society together to exchange ideas and to understand different aspects of the problems. Next, proposal under the consideration to ensure greater security are under formulation and will be presented to the state parties. Biosecurity and strengthening the BWC should be Biological Weapon Control Convention, in which the nanoparticles and all these particles can be controlled by this method. Assessment of their relevance to the expert. Material research will go beyond and will include cyber, robotics, artificial intelligence, 3D laser printing, extra. These are the new technologies which are making change. And the world will be different in 2030 by these new materials and new technologies. The solution is not to ban these products or stop material research, but rather to systematically study the safety and security of the materials and to ensure a communication flow between all stakeholders, mean industry, researchers, and policymakers. Okay, I will go straight to the last one. It is suggested international law is required to govern the safety and security of a material. The major hurdle is the disagreement on what exactly is to be regulated. Last point, the takeaway. Whatever I said, what is the takeaway of that? First, to remain in competition with the material research in the world. First. Second, it is a need to work on new materials for advancement and to adopt new emerging technologies where we should use. Third, researchers need top-class computer facilities for computation, predictions, and acceleration in material research. HEC should look into it if they want the material research to be done. And the last one, researchers should have free access to advanced material data banks of the world.
ये रिसेंटली जो एक आ गया है, मैं इसको कहती हूँ सिवाय स्केल के और कोई बात नहीं, नैनो मटीरियल जो क्रिस्टल स्ट्रक्चर होगा आंगस्ट्रॉम में, तो वो तो 10 टाइम्स छोटा है कंपेयर टू नैनो साइज. ठीक है जी. तो मुझे तो लग रहा है कि ये नैनो इज जस्ट अ स्लोगन, नथिंग एल्स। आप जब मटेरियल्स की प्रॉपर्टीज प्रैक्टिकली मेजर कर रहे होते हैं तो वही मटेरियल है आप बल्क फॉर्म में उठा रहे हैं, वही मटेरियल है मैं XRD को दे रही हूँ तो कम से कम आधा ग्राम तो होता ही है, तो वो बल्क फॉर्म में ही होता है। और जो नैनो मटेरियल हम कह रहे हैं वो एक स्केलिंग ही है, तो इसलिए ये जो मेरा ख्याल है कि वो स्केल इसलिए आ रहा है क्योंकि हम कहते हैं जी माइक्रो, ठीक हो गया, उससे पहले हम मिली की बात करते हैं, फिर मल्टीप्लाई बाय 10⁻³ और किया तो -9 मीटर हो गया, ठीक है। लेकिन ये जो हमारी बातें अक्सर होती हैं कि जी नैनो स्केल पे जाके मटेरियल की प्रॉपर्टीज़ चेंज हो गई, मुझे तो उसमें कोई ऐसी चीज़ नज़र नहीं आई, क्योंकि मटेरियल जब मैं उसको लैटिस कांस्टेंट को ही उठा रही हूँ तो जो प्रॉपर्टीज़ चेंज होनी है वो तो उसके लैटिस कांस्टेंट पे डिपेंड कर रही है। सो दिस इज़ अ क्वेश्चन विच कैन नॉट बी आंसर्ड सो क्विकली, but galaxy of scientists are sitting, so they should take home and we should think about it. Why we are saying so much big slogan nanomaterials, though the lattice constant is 10 times smaller than that scale. Thank you, sir.
इसका जो निटी ग्रिटी जवाब है वो तो मैं भट्ट साहब की तरफ रेफर कर दूंगा, लेकिन आपके सवाल का जनरल जवाब मैं देता हूँ, वो ये है कि I didn't absolutely talk about nanomaterials. I talked about, just a second, let me finish. I talked about the new materials, I talked about the smart materials, I talked about the materials. So this is one of the properties. Property can be different, millimeters, nanometers, anything. We are not concerned with the properties now. As a scientist, you have mentioned that. But basically, my lecture is to see the uses of those materials. What are the uses? Where they are used? I am not concerned about a 10 millimeter or millimeter or nanometer or something. Where they are used? Why they are used? Because they are used by their properties. And if they have the properties, they are used there. So this is the second answer. Third, we should go on their uses. As a scientist, you can suggest that they go there with this side, they go there with this side, and with this side we can use it. We can use these properties to our advantage. We are not concerned that why we define them like that and why should we define. And this is explained by the Bhatta in his lecture that initially they were called as advanced materials, they were called as smart materials, and in 1975 by the Japanese they are called as nanomaterials. So you can give the definition. I am just concerned about application.
Last talk before the lunch, that is by Dr. Rizwan Raza. He's an associate professor at ComCity University, Lahore. His PhD in energy technology with specialization in fuel cell from Royal Institute of Technology, KTH, Sweden. He has 16 years of experience in energy research and teaching. He has published over 200 papers, delivered 60 invited talks, and 30 different conference papers with an impact factor of 1,000 and H index of 38, number of citations 4,500, and edited 2 books, 10 book chapters. So please welcome Dr. Rizwan Raza.
Bismillahirrahmanirrahim. Assalamu alaikum. Thank you very much, Dr. Adnan, for inviting me. And I would like to thank also the conference organizer, Professor Ilyas, to discuss about my research area and about some of my research results. I will try to give overview what we have done and what we are doing. So, as you know, as per my title of my talk, I will discuss today about the climate change and what are the major challenges nowadays in the world, especially, you know, from last many years, there are many issues in the world they are discussing. I always discuss about one of the Nobel laureate quotation. He discuss about the next 50 years top 10 problem, and energy and environment are the top one. But nowadays, I mean, environment and climate change, of course, is correlated each other. And actually, the one of the major challenges is the climate change. What we are affecting here in Pakistan as well, but all over the world we are affecting. So how it can be, I mean, overcome or how it can be addressed with the, like is the theme of the topic about the smart materials. How can we play with the smart materials to address these issues, particular climate change and energy crisis? These are the two major challenges nowadays. So in my talk, I will try to cover these things. Especially I would like to thank Sir Khurshid, who discussed about the emerging technologies, smart materials, actually which make more easy to discuss about my topic today. So I will try to cover some more things, especially about two emerging technologies. One thing is about fuel cell, which is also called the clean energy technology. Another thing is chemical looping system. Actually, nowadays, after the, if I talk about the last 100 years, after industry revolution, you know, with the burning of fossil fuels, how much emission is there in carbon dioxide particular, and due to this, how much it affecting on the climate. So how it can be covered? Of course, there are many technologies. People are working in a different way. And one of the new technology which has been, I can say, is discovered in last 15 years from the one of the Swedish Professor Anders. Actually, recently I have completed one project with them in Chalmers University regarding this one. And he said we can control these carbon dioxide emission. In particular is a chemical looping combustion system and chemical looping gasification, actually two different technologies. So let's see. As I, based on my background on energy materials, so that's why I will discuss about some smart materials as well. So here you can see, I mean, one of the, our requirement nowadays in Europe also, before it was not like before COVID, energy crisis, but there are now also some energy crises are there. And energy and environment is also correlated each other. If you are getting energy from conventional system, from fossil fuels, then there is emission. And based on emission, you are going to pollute your environment as well. So first we have to address this existing system, our existing industry system, how there is lot of emission, how it can be controlled, and what are new technologies, either there is some emissions, so how it can be controlled, and then in parallel, some emerging technologies like renewable energy based, in particular fuel cell, which is also called the future technology. So first, on existing system, based on the burning of fossil fuels, there is a lot of emission, and we have to control and we have to capture those technologies, those things from this burning. You can see from this graph, in last 100 years, as I mentioned, from this to this, till now, how much is emission is there, and almost 1 to 1.5 degrees increase globally. Our Earth is, due to this global warming, the temperature is increased 1 to 1.5 is a different data is quoted. And one of the climate expert recently predicted that same temperature we are going to achieve in next 10 years. I mean, you can compare in last 100 years, we achieved, in negative sense, 1 to 1.5 degree. And next 10 years, again, it will increase from 1 to 1.5 degree. So how? Why? Because of this emission. So first we have to discuss about this our existing system, our existing power technologies, our existing power industry and other industry where is a lot of emission. So based on that, very famous conference in 2015 regarding the Paris Agreement, which is more famous regarding the Paris Agreement, where European Commission have discussed and they have agreed upon to give a new VN. Unfortunately, in Pakistan, we are not thinking about these things. A lot of senior professors are here. They know about things. But European Commission, they give this VN 2050, where they want to achieve 50%, in other words, is a CO2 emission reduction, 50%. But some countries, they have given their own VN, like Germany, France, and some Nordic countries like Sweden, Norway, Finland. They give, we should go for the negative emission. What is the called negative emission? Always emission is there. If emission is there, how it can be negative? So just for the students, negative emission like this way, from our industry or some other auto vehicles on the road or some other things from the conventional, the emission is there. What we are emitting and how much we are capturing, or what we are storing. So it means, if you are emitting 1,000 ton and you can capture 1,000 ton, it means there is a zero, like a simple equation. But if you are emitting 1,000 ton, but you are capturing more than 1,000, but how it is possible? If you are emitting 1,000 ton, how can it be capturing more than 1,000? Actually, the climate change and environment issue is not only for the one country, it is across the border. Emission can come from other side, like our emission can go to the neighboring countries, and neighboring countries can come some their emissions to our countries. So that's why they are thinking, from neighboring countries or neighboring area, if something is coming in the form of this emission, we have to capture also. So that's why they are thinking about the negative emission. So that's why here is some scaling of different countries like Sweden. They achieved zero emission till 21. Last year they achieved zero emission. What they are emitting and what they are capturing. But now they have planned till 25. Before, in Paris Agreement, they presented they will achieve in 2030, but now they have planned and revised in their policy. They will go for the negative emission till 2025. So you can see here is Sweden, Germany, France, and many other countries, how much they have achieved till now today, but where we are. So anyhow, there are a lot of things where we can play with these technologies and we can address these issues like smart materials, nanomaterials, and many other. I'm not going to discuss question about madam, but is a debatable. A lot of things can be discussed. But in science also, like in poetry, शायरी, कुछ अच्छे वर्ड्स इस्तेमाल किए जाते हैं फैसिनेटिंग, तो साइंस में भी करने चाहिए ताकि स्टूडेंट्स अट्रैक्ट हों, पता चले कि उसकी वर्थ क्या है. अगर सादा लफ्ज़ों में बयान किया जाए तो शायद उसकी वो एप्लीकेशन वर्थ ना हो सके. Anyhow, I'm not going to discuss on those things, but lot of nanomaterials people are working in different areas, particular in energy technologies. Many technologies are there. Renewable energy based in renewable wind, solar, biomass, and there is other now is a storage, energy storage issue based on energy storage. There is supercapacitor batteries and some other technologies also there. So first thing is, as I mentioned, my talk is based on two parts. First thing is on existing technologies, on existing industry system where we are getting emission is power industry. So chemical looping they have introduced. If we can integrate this system with our industry, we can capture CO2. 100% can be capturing. And this is a chemical looping can be defined like this way. Inherently, we can separate CO2 from this system. How? But I just can give you this from this figure idea. I mean, if there is one air reactor, another is a fuel reactor. In fuel reactor, if you can introduce some oxygen carrier materials, because in fuel there you have a CH4, biogas, or some other gases, then there is emission of carbon monoxide, CO. But when you are using oxygen carrier materials, it can donate a oxygen, and it can be CO2, and it can be easily separated from that system. So there is also some like in electrochemical devices, you know, the redox cycle, oxidation and reduction process, also in fuel cell and some other devices. So anyhow, based on this chemical looping, that professor also gave an idea how it can be implemented in industry, and they have already installed more than 100 projects in different industry, but they are planning till 2050 more than 3,000 projects for this one. In university, I mean, actually Shalmar University is almost, if I can say, more than 90% based on the industry funding. Unfortunately, we don't have here in Pakistan. So before, I just want to give my own opinion in industry and academia collaboration. Actually, काफ़ी डिस्कशन हुई, डॉक्टर दनान साहब ने भी सर ने भी उसको एड्रेस किया. तो one of the thing, we always, academician, professor, teachers, researcher, they are trying to get some problems from the industry, but we could not get. As mentioned, many examples from senior professor, actually our industrialist is not willing to come. They want profit in a day, what they have invested. But thing is that we propose like this way. If our policy makers from our government side, they should implement some kind of instructions to the industrialists. They should send us some kind of coordinator or any responsible, or they should make, every industry should have a R&D section, and that R&D section should collaborate with the industry. Otherwise, that industry should not be. Like our EPO, Environmental Protection Authority, EPA, they have I mean, without the environmental certificate, we could not open any industry. But similar way, without any R&D section, industry could not, can be work in Pakistan. So in this chemical looping system, what are the oxygen carrier materials, which are the main role? Nowadays, they are using the natural ores material. Natural ores, ilmenite, is a very common. Ilmenite is combination of iron, manganese, titanium, mostly these three components. Some ores like Egyptian-based, they are very common and more giving results in this chemical looping system. They are based on the iron titanium. Some Canadian ores, they have iron manganese base, but there are some impurities. But they have on how we can develop new materials of oxygen carrier. They have their own requirements. I'm not going in details. So, but of course, if oxygen carrier, then it should have a high oxygen carrier capacity. But they have a efficiency performance 1%, 2%. How it can be increased? So that's why my recent project was about this one, to develop synthetic ilmenite materials which can work efficiently in this system. And we develop, here I have mentioned 4 different, but as I mentioned, there is in fuel, there is a methane, biogas or some. Also catalyst can work very efficiently there. If we can introduce, before in ilmenite there is no any catalyst, we also introduce some kind of catalyst and its efficiency increase. Not going in again XRD function, which we have developed different oxygen carrier to see what kind of phases are there. I mean, iron based or titanium based. Actually, titanium is using as a supporting, but main role is there of oxygen. Fe2O3, it can be reduced and oxidized in air and fuel reactor. So the confirmatory, I can say the confirmatory test are the, how can we test this redox cycle for this material? Either it is stable or it can give you some more oxygen carrier capacity, how it can be calculated from the system. TG is the best tool. I mean, because air fuel reactor is working more than 800, 900 degree. So in this, we have used, here is one material which have 50% ratio of iron and titanium. Actually, titanium can stabilize also iron phase. So there is, first we have checked in the fuel syngas, and other is in methane. And methane is very stable, but oxygen transfer capacity in syngas is very good, because in methane there is some carbon deposition on the material, and then there is some agglomeration during this process, and there are a lot of challenges, also problems, but it can be catalyzed with a different catalyst material. So then it had been tested in different temperature, but you can see here is at 1000 degrees a very have a good redox cycle, and it can be seen from here the good oxygen transfer capacity. So anyhow, then we have tested in XPS which phases, mean Fe2O3 to F3O4 hematite to another phase, reduced phases, and it has been seen that it is also stable. So another, I'm just skipping this, we have introduced molybdenum as a catalyst in this oxygen carrier, and further its oxygen transport capacity has been increased till 9%. And then recently we are trying to integrate to make some hybrid system with the fuel cell and with this chemical looping system. Because in chemical looping system we can get also hydrogen gas after some reformation, if we are going for the reformation system or the gasification system. That hydrogen can be used in a fuel cell. So here is a mechanism how it can be donate oxygen vacancies from one part to another part. But I am going to discuss my second part, which I have more related to my PhD work as well, is the energy material. Why hydrogen energy is more important? As you know, hydrogen is a very, very clean fuel, and hydrogen is abundant in this universe. यानी हमारा जिंदगी का जो सिलसिला है इस कायनात का, वो पानी के साथ लिंक्ड है. पानी है, हम भी हैं, कायनात भी रहेगी. तो पानी H2O है. So we can get hydrogen always from there. But another thing is, I always say, the best utilization of renewable energy resources is the fuel cell technology. Why? Because in renewable energy resources, solar, they are dependent on some system. Wind, they are dependent also on some system. And one time it's have a good, another time it's not. But another time we can go for the storage system. But that storage can be in the form of hydrogen, and then that hydrogen can be integrated in the fuel cell system. So that's why it's the best utilization. So hydrogen energy, H2, hydrogen molecule, there is a one proton, one electron, and when it can be oxidized, there is a reduction process also. So if you can break the bond and you can get a proton, electron, and electron you need for your power system, for your electricity. So anyhow, another thing is the hydrogen have best fuel among other fuels. Why? It have higher energy density, 142 megajoule per kilogram. गाड़ी लाहौर से इस्लामाबाद आनी है, 1 किलोग्राम हाइड्रोजन इज एनफ, यानी उसकी हाई एनर्जी डेंसिटी है एज कम्पेयर टू ऑयल, पेट्रोल, डीजल एंड अदर थिंग. देयर इज नो एनी एमिशन, zero emission. So anyhow, lot of question for students for any new technology, where, why, when, what, how can we get these. But just to give for students how it can work, it's like a battery, 3 components, anode, electrolyte, cathode. On anode side, we can give a fuel in the form of hydrogen, and on cathode side, we can give a oxygen, or we can give directly air, because in air we have oxygen. So on anode side, oxidation, cathode side, reduction process, and here is only, just want to mention, as I mentioned, there is a 3-phase boundary on the interfaces of electrolyte and anode. When there is a hydrogen and there is a chemical reaction, oxidation process, then electron can pass through the circuit and proton can pass through the membrane. Actually, membrane is based on the proton conductor. And based on this electrolyte, it have a different types, alkaline fuel cell, phosphoric, molten, and solid oxide. Our more work, and in our lab, we are working on solid oxide fuel cell. Solid oxide fuel cell, why? Fuel cell have high electrical efficiency as compared to other power generation system. But among the fuel cell, solid oxide fuel cell have higher efficiency, more than 60%. I am talking about the electrical efficiency. But it is the main challenge, it is working at very high temperature, more than 800, 900 degree. Right now, what we have this kind of product, in particular in USA, Bloom Energy is working on this one. But it's working on 800 and 900 degree, and there is a conventional electrolyte is YSC, ETS stabilizer Konya. But problem is there, if we have a high temperature, there is also other accessories to assemble it and to make it more commercial. It's very expensive at very high temperature. So it's big challenge how to reduce its operating temperature. So for lowering operating temperature, when you lower its operating temperature, there are a lot of challenges again. There are a lot of losses, polarization losses. Among the polarization losses, mass concentration losses, ohmic losses, and activation losses. But ohmic losses are main important due to the materials, anode, electrolyte, and cathode. So those some conventional material have electrolyte, and electrolyte is a key component, and electrolyte should have a 0.1 Siemens per centimeter. But for this, to achieve this ionic conductivity, if we are going to reduce its operating temperature, we need some such materials which can work at very low temperature, and it can give you same ionic conductivity. So based on one of our project during my PhD with the European Commission with the different 5 countries, they agreed upon these 5 key points, how can be it reduced. Here one thing is about the interfacial material design. I'm not talking about the other things, but this interfacial design, based on that, we have designed one material coated with the existing electrolyte, doped ceria, with some carbonate material. There is some interface, and actually that interface can enhance the ionic conductivity. So just to cut another work from my PhD, she also developed, and here is a TM image where you can see where is the interface and where is a coated material, where is a core and core shell material, and how ion can pass through. We give the name highway for the ions, ion materials. So here is some impedance spectroscopy to check, and a lot of work have been published regarding this, but I want to mention this one. As I mentioned, among the many challenges, ohmic losses is the main challenge regarding the materials when you are going to lower its operating temperature. And also there is anode, electrolyte, cathode. There is some compatibility issues. Some high temperature based material people knows about that. If there is a different thermal coefficient of different components, when you can combine it, then there can be, when it can be a one device, it can be a problem, because they have a different thermal coefficient, device can be crack, or so there are a lot of challenges in 3 component. Just they are thinking about simple 3 component, but why not it should be a single component? So based on one article from Israeli professor in 90s, mixed ionic and electronic conductor, we see some kind of properties. We got that. Based on that, we develop a material, but we optimize an ionic conductor and electronic conductor. And we develop one single layer fuel cell, and it can work like a single page. One side can act surface, can act as a anode, other side can act as a cathode, surface, but it is a single component. So just based on the surface reaction. So not anode separate, not cathode separate, not electrolyte separate. So mixture. So anyhow, it has a same working principle, same advantages. Even at high temperature, there are other beauty is you can use other hydrocarbon, biogas, methane, ethanol, methanol, liquid-based, solid-based, gas-based fuels, hydrocarbon fuel-based, you can use there. So based on that, we published a lot of advanced energy, nano energy, energy environment. Even we submitted to Nature Nanotechnology, they gave us a name. Why not you can give it, it is a 3-in-1, from 3 to 1. So after that, we give name it. Its working principle is here. Actually, it is a mixture of ionic and electronic conductor. Gray are the ionic conductor, red balls are the electronic conductors. So there is a nano-redox reaction. Here you can think about the importance of the nano materials, I mean how it can work. I mean otherwise it was redox reaction on bulk material, but here there is a redox reaction on nano scale, I mean from particle to particle, from one ionic conductor to another electronic conductor. There is interface in any, you can say lot of interfaces, but here you can find there is a redox process. So I'm not going in detail. If somebody want to ask question, so can be discussed later on. So some work from our MS student, they have optimized and published lot of, one of just based on another project on silicon carbide, and just to give you about some recycling. So as in Pakistan, I mean, we are working on different things. Madam discussing about one small plate, what will happen after our eating, it will affect on also our environment and things. So we have not really thinking about our environment and not thinking about our waste material. So in the countries, I mean Sweden country, more than 99% waste material they are using in the recycling way and for the productive way in a different applications. But unfortunately here is no. So एक छोटी सी अक्सर मैं टॉक्स में कह रहा हूँ कि हर बंदे के पास मोबाइल है, लैपटॉप है, हमारे उसके अंदर क्या है, लिथियम आयन बैटरी है. तो बैटरी ख़त्म हुई तो हमने क्या किया, फेंक दिया, या किसी शॉप कबाड़िए के पास किधर गए. लिथियम भी बहुत रेयर है यानी बैटरीज में, और लिथियम कहाँ पे कह लें कि ये आफ्टर 2025 कह रहे हैं कि आफ्टर 25 में भी लिथियम ना रहे, इलेक्ट्रिक व्हीकल्स आ रही हैं तो क्या बनेगा. तो वी हैव टू रिसाइकल. यानी पाकिस्तान के अंदर इतनी पॉपुलेशन है, इतने हम मोबाइल यूज़ कर रहे हैं, लैपटॉप यूज़ कर रहे हैं, तो उस वेस्ट को इतना पोटेंशियल है. इंडस्ट्रियलिस्ट को आना चाहिए, और ये इंडस्ट्रियलिस्ट को एकेडमिशियन रिसर्चर ही बताएंगे कैसे इसको रिसाइकल किया जाएगा. हमने एक छोटा प्रोजेक्ट किया और उस पर प्रोजेक्ट सबमिट भी करवाया है. यानी देखते हैं क्या फंडिंग होती है स्वीडन के साथ और आवर फंडिंग एजेंसीज़ के साथ. तो इसके अलावा हमारे यूपीएस की वेस्ट बैटरीज़ हैं, उस पर एक पीएचडी स्टूडेंट हमने यानी वो काम कर रहा है ऑलमोस्ट नियर टू कंप्लीशन विद द जीसी फैसलाबाद. और इसके अलावा भी यानी बहुत से वेस्ट मटेरियल हैं, एग्रीकल्चर वेस्ट है, उसको यूज़ किया जा सकता है. हमने छोटे ये एग शेल की छोटी सी एग्जांपल हमारे अंडर ग्रेड स्टूडेंट ने किया कि एग्स हम रोज़ाना अभी नाश्ता करके आए होंगे, आमलेट खाए होंगे, बहुत से यानी उसके शेल्स कहाँ गए, वेस्ट हो गए. इसी इलेक्ट्रोलाइट जो फ्यूल सेल के अंदर है, इलेक्ट्रोलाइट, उसके अंदर हम क्या यूज़ कर रहे थे, सीरियम, रेयर अर्थ इज़ वेरी एक्सपेंसिव. गैडोलिनियम को अडॉप्ट कर रहे हैं, समैरियम को अडॉप्ट कर रहे हैं. तो कैल्शियम कैन बी एक्सट्रैक्टेड फ्रॉम दिस एग शेल्स, और ये एग शेल्स से कह लें कि कैल्शियम जो हमने मार्केट से परचेज़ किया वो उससे 10 कह लें कि 1/10 प्राइस में हमने उसको यानी अपनी लैब में बना लिया. यानी वो कह लें अगर 1000 रुपये का, तो ये इस पे कास्ट ऑलमोस्ट कह लें 100 रुपये आ गई होगी. तो यानी वेस्ट है, उससे हमने कैल्शियम कार्बोनेट, कैल्शियम ऑक्साइड एक्सट्रैक्ट किया, उसी को डॉप किया सीरियम में और उसको एज इलेक्ट्रोलाइट फ्यूल सेल में यूज़ किया. एंड आवर पेटेंट इज़ इन प्रोग्रेस फॉर दिस वन. तो इस तरह के रिसाइकलिंग मटेरियल काफ़ी हैं पाकिस्तान के अंदर. यानी ऑरेंज के छिलके हैं, केले के छिलके हैं, उनमें कहीं पे पोटाशियम है, कार्बोनेट है, कहीं पे कुछ है, और उनकी. तो ऑलवेज ये भी कहता हूँ कि थिंक ग्लोबली, एक्ट लोकली. हमें इंटरनेशनल रिसर्च से फ़ायदा लेना चाहिए, क्या क्या वो कर रहे हैं, और उसको हमने लोकल रिसोर्सेज की बेस पे काम करना चाहिए कि हम उसको कहाँ पे इम्प्लीमेंट कर सकते हैं. और रिसर्च करो, लॉट ऑफ कोलैबोरेशन. और ये एक लास्ट मैसेज होता है फ्रॉम माय स्टूडेंट, ये भी डेवलप किया कि लेट्स सेव द वर्ल्ड टुगेदर, कि कैसे हम मिल के क्लीन एनर्जी पे काम करके अपने इन्वायरमेंट को भी 1 गेट 1 फ्री एनर्जी पे काम करें, एनर्जी क्राइसिस को ख़त्म करने के लिए, लेकिन अपने इन्वायरमेंट को भी प्रोटेक्ट कर रहे हैं. थैंक यू वेरी मच.
एक तो ये है कि नैनो मटीरियल्स इट्स ये साइंस या फिज़िक्स में पर्टिकुलरली ये सिर्फ न्यूमेरिकल मेजरमेंट यूनिट्स हैं. अब नैनो से हम जाएंगे फेमटो में ऑटो, मतलब है ये कोई ऐसा नहीं है कि इट्स ओनली द मेजरमेंट विच इज़ इम्पॉर्टेंट. उसके हिसाब से नैनो मटीरियल्स, जो मटीरियल्स बेसिकली सब नैनो टेक्नोलॉजी वाले जानते होंगे कि बेसिकली अगर 3 डिमेंशंस में एनी 2 डिमेंशंस अगर नैनो साइज़ है तो दैट इज़ कॉल्ड नैनो मटीरियल. शीट्स हैं जो भी है, तो इट इज़ ओनली नेम, नथिंग. और स्मार्ट भी उसी में नैनो आ जाते हैं, बेसिकली मेजरमेंट्स हैं. دوسرا میں نئی ٹیکنالوجیز کا ذکر کرنا چاہتا ہوں. تھنگز آر گوئنگ آن. اب اسی میں میجرمنٹ سے اب پیکو ٹیکنالوجی از کمنگ اپ, اور اس کی سپٹمبر 2013 میں بک بھی چھپ گئی ہے, کوئی 600 پیجز کی بک ہے, جس میں پیکو ٹیکنالوجی کے متعلق کچھ ایکسپیریمنٹ سجیسٹ کیے گئے اینڈ سو آن. اور پیکو سیٹلائٹس مینز اگر ڈرون جو بہت بڑا ہے ویٹ میں, تو فیو گرامس 100 گرامس کا ڈرون چل رہا ہے, وہی کام کر رہا ہے جو. تو یہ تھنگز آر گوئنگ آن ان ڈفرینٹ ڈیولپمنٹ. تو یہ سمپلی میجرمنٹ نیمز ہیں. پیکو ٹیکنالوجی از کمنگ اپ ان اے بگ وے. تو اس طرح سے یہ ڈیولپمنٹ ہو رہی ہیں. نینو میڈیسن میں نئی میڈیسن, تو یہ اٹس اونلی اے میجرنگ تھنگ. اور بیسیکلی اصول جو اس کا یہی ہے کہ سرفیس ٹو والیوم ریشو دی پارٹیکل سائز پہ ڈپینڈ کرتی ہے. اسمالر دی پارٹیکل سائز, تو سرفیس ٹو والیوم ریشو جو ہے وہ امپروو ہو جاتی ہے, اینڈ دی پراپرٹیز become different on these smaller units of scale. So I just wanted to make this one or two comments. Thanks. But very nice lecture. اور اس میں بیٹریز میں there is a lot of research on the increasing the time of the working time of the batteries. میں وہ ریسنٹلی چائنا میں بیجنگ میں جو اکیڈمی آف سائنسز کا انسٹیٹیوٹ ہے, ویری ویل نون سینٹر, وہاں پہ گیا تو ٹنوں وہ حساب سے چھوٹی چھوٹی بیٹری پڑی ہیں ٹو انکریز دی لائف آف دی بیٹری. تو اسٹوریج آف نینو ٹیکنالوجی کمنگ اپ ان اے بگ وے, انڈسٹریل ان آل ویز. تو اس پہ انڈسٹری کے ساتھ آپ اس کو کریں, اٹس ویری امپورٹنٹ. یس, تھینک یو.
ایک میرا بھی سوال ہے, وہ یہ ہے کہ آج کل جتنا فولڈیبل آ رہے ہیں نا موبائل, اتنا بیٹری پہ بھی کام ہو رہا ہے جو فولڈیبل ہوں گے.
سویڈن میں یعنی اپسالا یونیورسٹی میں اس میں ایک پروفیسر ہے, اس کو یورپین کمیشن کی بہت بڑی فنڈنگ ملی. دے آر ورکنگ آن فلیکسیبل بیٹریز. تو میرے ایک کلیگ ہیں ڈاکٹر عامر رزاق, دے آر ورکنگ آن دس. ہم بھی بیٹریز پہ, ہم سالڈ اسٹیٹ بیٹریز پہ کام ہم بھی کر رہے ہیں, لیتھیم آئن بیٹری اور سوڈیم آئن بیسڈ بیٹری. اس پہ کافی سوڈیم کا, لیتھیم کی ریپلیسمنٹ سوڈیم سے کر رہے ہیں, اور سوڈیم پاکستان میں بہت زیادہ, نمک بھی ہمارے پاس ہے. تو یعنی وہ فلیکسیبل بیٹریز کا ہے کام کر رہے ہیں. تو اور بھی آئی تھنک کہ نسٹ میں بھی ہیں, وہ میرے خیال میں ڈاکٹر غلام علی وہ بھی کام کر رہے ہیں جو میں جانتا ہوں. اس کے علاوہ بھی کافی ہیں, لمز میں بھی ہیں ایک بیٹری کے, وہ ڈاکٹر شعیب آئی تھنک کہ وہ کینیڈا چلے گئے ہیں شاید پوسٹ ڈاک وغیرہ کے لیے.
There are two things which I like to mention here. One is the carbon dioxide absorbers you talked about. I was in a meeting and I was talking about the environmental minister here. Recently, when we are going to net zero emission and zero emission, we bought some carbon dioxide fuel energy producer of the coal. We are using fossil fuels. And I questioned him that whether we are buying the carbon dioxide absorber with them or not. We are not buying even the carbon dioxide absorbers with the coal plants. So when you are talking about environment, this is very important. Second, I like to support your progress and your project. When you talk about wind energy, you talk about solar energies, you talk about the batteries there. And these energies are dangerous in that sense because they are using very big batteries in which they are using lithiums and other rare earth gases. So this is one of the points.
Yeah, thank you very much, sir. That's why in California, they have established hydrogen station directly based on solar system, and they have introduced the fuel cell vehicles, not directly storage in the batteries because they need a lot of batteries. Even in one of project few years back, Navy Admiral, they invited us and we visited there in Karachi, and they show us in submarine they have a very heavy battery, and they submarine they have used in 65 watt and 71 watt, and the submarine almost is length is more than this auditorium, and all is full of the batteries. اس کا ویٹ جو سارا ہے وہ اسی کی بیس پہ. تو دے وانٹ ٹو ریپلیس دیٹ ون کہ وہ کس طرح اس کو یوز کیا جا سکے ڈائریکٹلی. لیکن اینی ہو از اے گڈ پوائنٹ. بیٹریز جو ہیں ان کو اسٹور کرنے کے لیے ان کے ساتھ جو ہائبرڈ سسٹم یا انٹیگریٹ کرنا ہے تو وہ از اے ویری ہیوی. سو دیٹس وائی آلسو ان ایز آئی مینشن ان کیلیفورنیا دے یوز ڈائریکٹلی پروڈکشن آف ہائیڈروجن, کہ اس کو ڈائریکٹلی جو ہے سولر جو ہے جو ایکسیس ہے اس انرجی سے وہ ہائیڈروجن بنائیں اور اس ہائیڈروجن کو ایز اے فیول फिर यूज़ करते जाएँ डिफरेंट व्हीकल्स में। 1000 व्हीकल्स दे आर रनिंग ऑन द रोड इन कैलिफोर्निया, वो उस हाईवे पे उन्होंने डायरेक्ट
some shields to present. I request Dr. Zafar Ilyas to come upon the stage for the shields to be presented.